Hello, everybody. It's good to be here. My name is Marcus Noack. I am with Lawrence Berkeley National Laboratory and a group called CAMERA, the Center for Advanced Mathematics for Energy Research Applications. And that is located in the San Francisco Bay Area in California in the United States. Today, I wanted to give a quick overview of autonomous experimentation at large-scale experimental facilities. And I will now share my screen. Here we go. The topic is optimal autonomous data acquisition for large-scale experimental facilities. So again, I'm with CAMERA, the Center for Advanced Mathematics for Energy Research Applications, but this work has many collaborators around the globe. So I want to get started by really at a high level talk about what is autonomous data acquisition in general. I want to talk just a little bit on a very high level again about the underlying technique, which is mainly uncertainty quantification based on what is called a Gaussian process. And we're going to see what that is. And also look at a few examples. And in the end, I want to give you just some tools so that you can do that yourself at home or at your home institution. So let's get started. What is autonomous data acquisition? Overall, when I got into the field, I saw a lot of big instruments, very expensive instruments being operated manually by humans. So we always have an instrument. In this slide, it's an example of a synchrotron light source. The synchrotron light source, just like a microscope or a neutron scattering beamline or a spectrometer, depends on certain parameters. Knobs you can turn, if you will. And the sample that is being probed also depends on a set of parameters. Synthesis parameter, processing parameter, and environmental conditions. And what comes out of any experiment is some sort of high-dimensional structure. In this case, a detector image, but it could be a video, it could be a spectrum. But any piece of information coming out of these experiments is really, they are all functions over some parameter space. And the parameter space is the space spanned by all the parameters going into the experiment, the processing parameter, environmental condition, and the instrument-related parameters. Often the detector image goes then into an automated data analysis that is often pre-existing when I work with these, with the groups and with their instruments. But then as I came into this field, it was about 5 years ago, again, often a human scientist would use intuition to figure out what to do next, looking at some data, and then basically saying, how do I navigate through this parameter space? Because the scientific result is really having a model across environmental synthesis and instrument parameters. And the human would try to figure out trends and patterns, and then try to go in directions of this parameter space that seem interesting, or where the scientist deems a favorable characteristic of a material to be present. Then the instrument is steered to these areas, the right sample is prepared, and then the measurement is triggered. Again, this is what I call an intuitive-based experimentation. It's clearly not autonomous. Human attention is required the entire time. There is no real metric for quality. Usually we are just running out of instrument time. And it relies heavily on past experience, and there is a lack of reproducibility. There are other methods that are being used in very low dimensional spaces. So for instance, if I'm just looking through a range of temperatures or a combination of temperature and pressure when I make the sample, for instance, I could do a scanning approach. In 2D, that still works. I could imagine having 100 steps in each direction. It would be 10,000 scanning steps, so that would work. That is automatic, so nobody has to sit there, but there's certainly no intelligence involved. And there's, again, no metric for quality. And the same is true for random point selection. There, the space can be probably a little higher dimensional, but if we go too high, then the quality will just decrease of the model. And there is, again, no real metric for quality when we stop. Instead, what we have developed is an intelligent decision-making algorithm that, after a few data points have been seen, can do uncertainty quantification and then make intelligent decisions autonomously what an